Alrighty guys, so we are a little behind. We were supposed to do this last time, but I felt like the material from 5.1 was a whole lot for y'all to handle. So I decided to split it up and give you a little extra time on it. So what I have here is chapter 5.2. So I split it into two lectures instead of putting it into one. We're doing logarithmic functions instead of exponential functions. So to start out, we're going to connect the two. It says find the inverse of the exponential function. So the exponential function is y equals b raised to the x. So the first thing you got to do to find the inverse is switch your x's and your y's. So we've done that in this step. Now we have to solve for our y. So we've got a y in the exponent here. We need to get that y out of the exponent. There's a couple ways you can do this. This is the way that I chose to do it. There are several different ways, and there's plenty of methods that we're actually going to learn in this chapter in order to do this. But the method I chose was to take the log base b of both sides. If you know anything about logs coming into this, the log base b of b is 1. So that'll essentially cancel itself out, and you'll be left with a y. That's where this y comes from. Now the log base b of x, there's no way that reduces. So what you wind up with is this y equals this log base b of x. That is called your logarithmic function. So the logarithmic function is essentially the inverse of the exponential function and vice versa. So the definition of a logarithmic function. For x greater than 0, b greater than 0, and b not equal to 1, the logarithmic function with base b is y equals log base b of x, which is defined by x equals b raised to y. Now, let's convert from exponential to logarithmic form. So in our first couple of examples, we've got quite a few here on your worksheet. We've got at least a through d. We've got a says 3 squared equals 9. B says 4 to the negative 1 equals 1 over 4. C says 5 to the first equals 5. And D says x equals 3 to the y. Now let's convert those from exponential to logarithmic form. I'm going to put this on the board. Alright, so if we take what we really just did, the very first thing we did, we've got y equals b raised to x. That's the exponential form. If we hadn't have switched our x's and y's to find the inverse, if we'd have kept them the same but solved for x, what we would have wound up with was x equals log base b of y. So that's basically a reverse solve for x. So if you're a formula kind of person, if I want to go from here to here, and whatever's in this exponent needs to go here. Whatever is the big number here needs to go on the base. And then this y here needs to go here. So this 9 goes here. The way that I remember it, and the way that it works for me, and it's the same thing. Log base 3 of 9 equals 2. That's just the pattern that works for me. Log base 3 of 9 equals 2. So if I come down here, log base 4 of 1/4 equals negative 1. If you're a formula person, use formula. If you can just follow the pattern, though, it's really easy. Log base 4 of 1/4 equals negative 1. So here, log base 5 of this 5 equals 1. D, log base x, log base 3 of x equals y. You gotta be careful if the function gets turned around. Don't just jump to the first one. The log base has to be what your base is here. And it's that easy. So you just keep it straight. You can use the formula, you can use the process. Just remember, if these get switched, don't mess up, we should be good to go. Going from exponential to logarithmic forms. Naturally, if we're going to convert from exponential to logarithmic form, we're going to wind up converting from logarithmic back to exponential form. So that's what our next set of examples are. So we've got 3 here. We've got log base 2 of 16 equals 4. Log base 10 of 0.0001 equals negative 4. And log base 6 of 1 equals 0. So let's put these on the board and convert them from that logarithmic form back to the exponential form. Alright, so uses the same two formulas over here. We're going from this one back to this one. So if you're a formula person, you can say, okay, whatever goes here is my base. So what I've got here, my base is 2, and it's raised to this x, which is a 4, and that's going to equal my y. My y is whatever is on the inside of here, which is 16. What I like to do, because I think it's a little simpler than that, is just kind of learn the process. 2 raised to the 4 equals 16. 2 raised to the 4 equals 16. That easy. 2 raised to the 4 equals 16. That's how I keep it straight in my mind. So if I'm here, 10 raised to the negative 4 equals that. 10 raised to the negative 4 equals 0.0001. Alright, C, 6 raised to the 0 equals 1. Makes sense because anything raised to 0 equals 1. And it's that simple. Next up, we've got evaluating logarithms. It says write y equals log base 2 of x in exponential form. B says use the exponential form from part A to find y when x is 8. C says evaluate log base 2 of 8 equals 3. D says evaluate log base 4 of 1 over 16. E says evaluate log base 10 of 0.001. So let's do all of these on the board real quick. So the very first one was write in exponential form. 2 raised to the y equals x. Pretty easy. 2 raised to the y equals x. Find when x equals 8. 2 the y equals 8. Okay. 2 times 2 is 4 times 2 is 8. So 2 to the third is 8. Therefore, y equals 3. Okay, the next one said, find log base 2 of 8. See what it equals. Okay. So, log base something to the 8th, and I think your question even gives it to you. It's supposed to be a 3. It pulls directly off of this. If you wrote this in the other form, so 2 to the third equals 8. If you wrote this in exponential form from here to here, that's what you would get. If you wrote this, which is essentially what you have here, and wrote it back to logarithmic form, that's what you get here. 2 to the third is 8. 2 cubed is 8. It's that simple. Now D, we need to evaluate log base 4 of 1 over 16. Okay? So a lot of times it's easier to convert it to exponential to evaluate it. 4 to the x equals 1 over 16. Okay? You look at that, you're like, okay, 4 squared is 16, but the 16's on the bottom. What do? Well, you have to remember that if I have a negative exponent, it brings it to the bottom. So what I'm looking at is 4 to the negative 2 equals 1 over 16. So your answer here would be negative 2. Alright, if you need more explanation for that, and some of you I'm sure do, because some of you I'm sure haven't messed with exponents like that, really hardcore like you should have in high school. If I have something that has a negative exponent, so 4 to the negative 1 is the same thing as 1 over 4. It's negative, just basically pulls this whole thing to the bottom, leaving the 1 on top. 4 to the negative 2, obviously, is going to be the same thing as 1 over 4 squared. 4 squared is 16, so it's the same thing as 1 over 16. E says evaluate log base 10 of 0.001. Okay? So, if I'm thinking about it, I'm like, okay, that means 10 raised to the something, we'll say x, equals 0.001. Alright? I got 3 decimals here. 1, 2, 3. 10 raised to the negative 3 equals 0.001. Don't believe me? Type 10 to the negative 3 in your calculator. It's going to give you just that. Alright? Easy enough. Now what I'm going to do is I'm going to go to your calculator and I'm going to show you how to type a few of these in so that you have a way to check yourself. So, back at the computer. So I told you I was going to show you on the calculator how to do log or log base. You should have log base on your TI-84 calculator. So what I did, if you didn't see what I just did, I'll start over. Hit the math button. And under math, I just scrolled down. And I've got log base. Okay. So for like part C, we had log base 2, 8. Log base 2 of 8 is 3. D, we'll hit math again. Scroll down to log base. Log base 4. Oops, that is not a 4. Log base 4 of 1 over 16. That's negative 2. And the last one, math, log base. Log base 10 of 0.001 is negative 3. So if you want to use your computer to check, or your laptop, or not your laptop, your TI-84 to check you can very well do that very easily. Next part of our note says graph y equals log base 2 of x, or 2 raised to the y equals x. So this is the logarithmic form, this is the exponential form. Obviously, we have to have it in a y equals format for our TI-84. So I'm going to graph the first one. It's the same thing. Alright, so I'm going to come over here, log base 2 of x. So y equals math. Let's scroll down to log base 2 of x. And I'm going to hit the graph button, but first I'm going to do zoom standard. So your log base function essentially is a shape like that. So if you got some space in your notes, you might want to sketch out a simple picture of this log base function so you have a general idea in your mind of what it looks like. Now just like the exponential function, the logarithmic function here, we've got all this information about it. So your equation is y equals log base b of x. Your x-intercept is 1, 0. Your y-intercept, you don't have any. It actually doesn't hit the y-axis. The domain is where x is greater than 0. The range is all real numbers in this case. The vertical asymptote is the y-axis. So if you remember, in your exponential functions, you had a horizontal axis, or your horizontal asymptote on the x-axis. Here, for the logarithmic functions, it's kind of the opposite. You have a vertical asymptote on the y-axis. Okay, so we've got two cases, and we're going to need to sketch them out. So case 1 is where b is greater than 1, and case 2 is where 0 is less than b is less than 1. Okay, so I'm going to go to the board and sketch these two cases out for you so that you can have them and you can see them, and we will go from there. Ladies and gentlemen, we have two cases. First case, when b is greater than 1, we've got this line that approaches the y-axis down here, but it never touches it. Remember that you have an x-intercept at x equals 1. Now, if b is between 0 and 1, actually what's going to happen is it's going to flip and it's going to go the other way. So you still have an asymptote on your y-axis. It still hits here at x equals 1, but it flips. Okay? So, this is concave down, this is concave up. You want to think about it like that. You want to say flipped up and flipped down, however you need to remember it. You got two cases. This is what it could look like. Obviously, it can shift depending on some stuff, and it can go up and down depending on some stuff, and we'll go through a little bit of that here in a minute. But these are essentially your two cases. If b is between these two numbers, it's going to look like this. If b is greater than 1, it's going to look like that. Further emphasize that, I have it here on a very nice screen. So, here I chose log base 2 of x, and I chose log base of a half of x, or 0.5x. I graph both of those. The blue line is your log base 2 of x. Your log base 0.5x is your red line, and as you can tell, they approach the y-axis, they don't touch it. They do continue to go, even though you can't really see them. And what you get here is they both hit at x equals 1. Back to the notes. Because our number system uses base 10, logarithms with a base of 10 are called common logarithms. So log base 10 of x is the same thing as log of x. So if it just says log of x, it's assuming that you have a base of 10. Now, we're going to write the equation y equals log x in exponential form and find y when x equals 10,000. Okay, let's do that example really quick. So let's put it in exponential form. This raised to this equals this. Remember, there is an imaginary 10 sitting right there. So 10 to the y equals x. Okay, so if x is 10,000, 10 to the y equals 10,000. Let's think through this. 10 times 10 is 100, times 10 is 1,000, times another 10 is 10,000. So y has to be 4. That's simple. Alright, next it says explain how the graphs of each compares with the graph of y equals log x. Okay, so A says y equals log of x plus 3, y equals 4 plus log of x minus 2 is B, and y equals 1/3 log of x is C. And then we'll get into natural logarithms after we do these 3 examples. I'm going to write these on the board and show you the answers. We work through them the same way we do with any other shifts and stretches and compresses. And then I'm going to show them to you on the calculator so that you can see each of them move. So, let's use the knowledge that we've learned in the past couple sections and chapters. It's on the inside. That means it's going to move left or right, right? So, it's a positive on the inside here, so it's actually going to move to the left. Okay, so it's moving to the left 3 units. Easy enough. Here, we've got 2 shifts. We've got a shift on the inside and a shift on the outside. Shift on the outside is either up or down. It's positive, so it goes up. So we're going to shift 4 units up. And we're going to shift 2 units right. See, we're not shifting. We've got a fraction here out front, so we're compressing. So it's compressed by a factor of 1/3. Now let's look at it on the calculator really quick. I've got them all typed on the calculator. Your original function was log of x. Your second function was log of x plus 3. Your third function was 4 plus log of x minus 2. And your fourth function was the third log of x. So our first function is blue, our second function is red, our third function is black, and our last function is a magenta pinkish color. So if we graph those, it pops up pretty quick. So if we graph those, our first function is this blue function here. Now on the board we said to get to our second function, we're going to shift left 3 units. Makes sense. We shifted left 3 units. Now we're going to start back at this blue function and try to get to our second function for part B. It says we need to shift up 4 units and then right 2 units. Makes sense. Looks like we did it right. Now for part C, it says that we have compressed by a factor of 1/3. So you notice that this line, this blue line, kind of goes up here, right? Now compressed means we kind of flattened it, right? So you can see that this pink line right here is much flatter than that blue line. Almost like something got laid on top of it and kind of flattened it down. So it has been compressed. So you can use your calculator to somewhat verify your assumptions there as well. Now, natural logarithms. Natural logarithms are the logarithmic function with base e. So that is y equals log base e of x. And it's defined by x equals e raised to the y for all positive number x, and denoted by the natural log of x equals log base e of x. So if we're using the natural log, we're going to use ln instead of log base e of x. That's just the notation for it. E is just a number, okay? So don't let e freak you out. It's a number. You can find it on your calculator. It's got a button. You don't have to memorize the number for e, anything like that. But if we're using e as a base, we're going to use natural log, okay? If you want to go through and type log base e of x, it'll work fine on your calculator, but the notation you're going to see for an e base is natural log of x. So the first example we have here says projections from 2010 to 2050 indicate that the percent of U.S. adults with diabetes can be modeled by p of x equals negative 12.975 plus 11.851 natural log x, where x is the number of years after 2000. What does the model predict the percent of U.S. adults with diabetes will be in 2022? Okay, so what we can do is we can go through and we can solve this by hand, which I'll do on the board real quick, and then we can solve it on the calculator. So let's go to the board first. All right, so this is the equation. Our initial year is 2000. The year we're wanting to find is 2022. Means we need to find the difference, which is going to be 22. That 22 is what I'm going to plug in for this x, so that my new formula looks like negative 12.975 plus 11.851 natural log of 22. Okay. I wanted to show you how to find the x to use there, show you how to plug it in. Some of y'all are still struggling with that. Now let's put it on the calculator and find us an answer. Alright, so I'm going to type it in negative 12.975 plus 11.851. The natural log button is right next to the 4 button. Just hit it one time and then type 22, close your parentheses, and your answer is going to be 23.66 if you're around the 2 decimal places. Now what you could have also done, I always like to give you alternate ways to do stuff. What you could have also done is come up here to y equals, cleared out all your old stuff, type that formula in, negative 12.975 plus 11.851 natural log of x. You could have graphed it. Now I can already tell you x is 22. We don't have a 22 on this. It's not big enough, so I'm going to need to zoom out at least one time. So I'm going to zoom out. Hopefully I've got 22 marks in there. We'll know soon enough. I do second calc value, x equals 22. I hit enter, and there it is. X equals 22, y equals 23.66 approximately if you're around the 2 decimal places. So you got a couple avenues to work that one. This is probably my favorite part of the whole lesson here. Logarithmic properties. So for b greater than 0 and b not equal to 1, we've got the log base b of b is 1. Second rule, log base b of 1 is always 0. Third rule, log base b of b raised to the x is always x. Fourth rule, b of log base b of x equals x. Number 5 says for positive real numbers m and n, if m equals n, then the log base b of m equals the log base b of n. Okay, really simple properties. Hopefully you've seen those before. So let's use those properties to evaluate the following. Those are the simple properties. We get to a few more complex ones here in just a little bit. Let's evaluate these to start with. So I've got A through F here. So let's do all of these on the board. First one is log base 5 of 5 raised to the 10. The second one is log base 4 of 4. C says log base 4 of 1. D says log base 10 of 7. E says natural log of E raised to the 3rd. F says log base or log of 1 over 10 to the third. So let's do this on the board real quick. Alright, so the first one. If you use your properties, this one's really easy. If you use your properties, you should see the answer is 10. If you want some verification for your properties, 5 to the 10 equals 5 to the 10. So you know that 10's the correct answer. Okay? 4 to the what equals 4? 4 to the 1 equals 4. We'll check it. 4 to the 1 equals 4. That's right. So 1 is indeed your correct answer. Or you could just use your properties. 4 to the what is 1. So 4 to the what is 1. 4 to the 0 is 1. So your correct answer would be 0. Okay? These are really, really simple. Log of 10 to the 7. Now it's a little more tricky, but it's really not that tricky. Okay? So, you got to remember that we have an imaginary base of 10 here. It doesn't tell you the base is assumed to be 10. So, log base 10 of 10 equals, or to the 7. So, we follow what we did here exactly. We know that the answer is just going to be 7. 10 to the 7th equals 10 to the 7th. You want to check it. But it's alright. 10 to the 7th equals 10 to the 7th. Our answer here is 7. Natural log, the base that you imagine to be here is an E. The E's. Natural log and the E essentially cancel each other out. You have a 3. Right? It works the same way that this base does here. Natural log has a base of E. That essentially cancels all that out. You're left with a number here. Let's cancel that out. You're left with a 3. F. F is a little tricky. Okay. Let's rewrite F. You need to be able to see that you have to rewrite F. Okay. I'm not really sure what to do here. This doesn't fit in. My property is really close. But if I adjust what's on the inside, it'll definitely fit my properties. So I've got log. If I bring this 10 up to the top, I could rewrite this 1 over 10 to the third as 10 to the negative third. Okay? Log of 10 just kind of cancels itself out. Right? Log of 10 just kind of cancels itself out and leaves me with that negative 3. Easy as that. Or you could say imaginary 10 here, log base 10 of negative 3 equals 10 to the negative 3, if that's how you want to think about it. So your answer for this one is 3. Your answer for this one is negative 3. Those should be really, really simple. Got some additional properties here. It says for b greater than 0, b not equal to 1, and k a real number, and n positive real numbers, then the log base m, or the log base b of m times n equals the log base b of m plus the log base b of n. That's the product property. 7 says the log base b of m over n equals the log base b of m minus the log base b of n. That's the quotient property. 8 says the log base b of m raised to the k is the same thing as k times the log base b of m. That is the power property. You really need to know those properties. Okay, I really like examples like these. Like so, those last 3 properties are some of my favorite logarithmic properties. So you really need to be prepared to use them, and they're not that hard. In the example we have here, I believe we have A through E to do, and we're going to do them on the board. I'll read through them first. It says rewrite each of the following expressions as a sum, difference, or product of logarithms. Simplify if possible. So for A, we've got log base 4 of 5 times x minus 7. B, we have the natural log of e squared times e plus 3. C, we've got log of x minus 8 over x. D, we have log base 4 of y to the 6th. And E, we have natural log of 1 over x to the 5th. So let's do all of these on the board really quick. So we want to expand these as far as we can. So we've got a multiplication here, a multiplication of 5 times this x minus 7. So what I can do is I can say, okay, that's the same as log base 4 of 5 plus the log base 4 of x minus 7. Okay. Now, I can't do anything with this inside. We don't have a property for addition and subtraction on the inside. We just have it for multiplication and division. So this is essentially as far as I can go for part A. That would be your answer. For part B, we've got the natural log of e squared times e plus 3. Okay, I've got a multiplication here. So I can simplify this to natural log of e squared plus the natural log of e plus 3. Now, I've got, you could do this a few different ways. The easiest way is to notice that I've got a natural log of e. So the natural log of e kind of cancels itself out, and I'm just left with this 2. So, I've got a 2 plus the natural log of e plus 3. There's nothing I can do with this e plus 3 because there's an addition there, and I don't have a property to deal with that. So my final answer for B would be 2 plus the natural log of e plus 3. C, we've got the log of x minus 8 over x. So I can rewrite this one, log x minus 8 minus the log of x. Okay, I can't do anything with this piece or this piece. That's as simple as it gets. D, I've got log base 4 of y to the 6th. I can use my power property. So I can bring this 6 forward. It's the same thing as 6 log base 4 of y. That's as simple as I can make that one. E, okay, so you can do a few things on E. Alright, so you could say, alright, that's the natural log of 1 minus the natural log of x to the 5th. Okay, natural log of 1, that's the same thing as log base e of 1. Anything that you have here, the log base anything of 1 or the natural log base anything of 1 is just 0. Okay, now I can use and bring this 5 to the front because it's an exponent. I get 0 minus the natural log of x, which gives you negative 5 natural log of x, and that's as simple as you get. If you wanted to, you could approach that one in a few different ways. So the other way that you can do it, I'll do it here in blue. You can say, okay, that's the same thing as the natural log of x to the negative 5, which is the same thing as negative 5 natural log of x. If you wanted to take that method as well. Either way, your final answer would be negative 5 natural log of x. This set of examples, it says rewrite each of the expressions as a single logarithm. So we've got A through C on this first part of these examples. A says log base 3 of x plus 4 log base 3 of y. B says 1/2 log base, or 1/2 log A minus 3 log B. C says natural log of 5x minus 3 natural log of z. So let's see if we can express all of these as a single logarithm. Let's go about expressing these as a single logarithm. They have to have the same base in order to combine them. Here we've got the same base. The base is 3. Log base 3. They're added here. The two logs are added. That means I can multiply the inside. But I can't quite do that because I have this 4 right here. In order to do that, it needs to be strictly log 3 and log 3. I can't have this 4. So let's go ahead and put this 4 as an exponent back on this y. That's one of our properties. Log base 3 of x plus log base 3 of y to the 4th. Now I've got my log 3's by themselves with the stuff on the inside, and I can combine that inside stuff. So the log base 3 of x times y to the 4th. There's your single logarithm. For B, and like I said, these logs have to be the same. I have a 1/2 log here, I have a 3 log here. The insides aren't the same, so I can't combine them there. I have to bring these exponents in before I can do anything. So, first step, I've got log. I've got a to the 1/2 if I bring that and make it back into an exponent. Minus, if I make this an exponent, I've got log b to the 3rd. Okay. Now, there's a couple ways you can do this, so if you choose a different route, as long as you get the same final answer I've got, that's fine. I'm going to rewrite this a to the 1/2 as the square root of a. A to the 1/2 and the square root of a are the same thing. So I'm going to do that in my next step. I'll go ahead and do it. It's really not that big of a deal. If you leave it as a to the 1/2, it's not a huge deal. But I'm going to write it as square root of a. Now, this subtraction here, I've got the logs kind of by themselves and then the stuff on the inside. So this subtraction means I divide them. So I've got log square root a over b to the 3rd, and that is all on the inside of that log. So that's your single logarithm there. C, I've got a natural log. Okay, like I said, the natural logs have to kind of be alone by themselves. They can't have anything out front. This one's got this -3 to deal with. So here we left the negative alone and just pulled the exponent, the number, and put it back up top. Here I'm going to show you the other way you could go about it, and you could have answered that one. So I've got the natural log of 5x. Okay, I'm going to pull this -3 and put it as my exponent here. So I can say plus natural log of z to the -3. Okay. This is a different method than what I used here. If you like this method better, stick with this one. If you like this one better, stick with this one. Now I can combine these. I've got this addition, so I can multiply. I get natural log of 5x times z to the -3rd. I can't have a negative exponent. So what I need to do is do natural log of 5x, bring that z to the 3rd to the bottom so that exponent can go back positive. And what I get is my answer is the natural log of 5x over z to the 3rd. And it's that simple. In this next example, we'll do A first on the board by itself, and then we'll come back and do B and C on the board together. A says use log properties to estimate the natural log of 5e if the natural log of 5 is approximately 1.61. So let's do that. So this is actually one you can type in your calculator and you can approximate the answer. That's not what it wants you to do here. It wants you to take the information and solve it on your own without using a calculator. So if I take this natural log of 5e, all I have is this natural log equals 1.61. And obviously I need to get a natural log of 5 by itself. Okay? To do that, I can use my property that says if I multiply on the inside, I can add if I split them up. So I've got a natural log of 5 plus a natural log of e. Okay? So, I've got a natural log of e. Natural log of e should just be 1. Use your properties. So I got a natural log of 5 plus 1. If I substitute this 1.61 approximately in for this natural log of 5, what I wind up with is 2.61. That's how they want you to approach a problem like this. Now, let's jump back. Let's do B and C. B says find log base A of 15 over 8 if log A of 15 equals 2.71 and log A of 8 equals 2.079. C says find log A of 15 squared over the square root of 8 all to the 3rd if log A of 15 equals 2.71 and log A of 8 equals 2.079. So, let's do both of these on the board. Alright, so I can't use my calculator bailing out here because I've got this A here. So you really have to know the process of how to do these. Pay attention. Alright, I need to get log base A of 15 and log base A of 8 somewhere kind of sort of by themselves. I've got a division here. So if I wanted to split this up, I could say that's the same thing as log base A of 15 minus log base A of 8. So essentially what I have is 2.71 minus 2.079. Okay, I've got the calculator here. I'm sure you have yours sitting right next to you. 2.71 minus 2.079. We get 0.631. You can do that pretty easy on your calculator. Those are easy numbers. Alright, part C, there's several approaches that you can use. So don't think that you have to use the approach that I'm using. If you've got a different approach, as long as you get the same final answer, it's more than likely fine. Because there are 3 or 4 different ways you can do this one. I'm only going to do it one. As long as you get the right answer, I'm okay with it. So, what we've got here, I'm going to go ahead and bring this 3 to the front. So I've got 3 log base A of 15 squared over the square root of 8. Okay, I've got a division here, so if I want to, I can split this up by subtracting. But I've got to keep 3 log a with everything. 3 log a 15 squared minus 3 log a to the square root of 8. Okay, I'm getting really close to what I need here. I need a log base a of 15, a log base a of 8. I've got a square root to worry about here, and I've got a square root to worry about here. I can get rid of this square root pretty easy. I can bring it to the front, multiply it times that 3. So I get 6 log base a of 15. I'm going to do an extra step over here just so that you see it. I'm going to change that square root to a half. If I do that, I'm going to just rewrite this first part. I'm going to bring that half forward. 3 times a half is just 3 over 2 log base 8. Okay. Now I've got what I need. I've got my 2 parts. I can substitute in for this, and I can substitute in for this because they're kind of by themselves. They're just multiplied by a constant. So what I've got here is 6 times, I'm going to substitute in 2.71 for this log base a of 15 minus 3 over 2 times 2.079 in for that log of 8. And you do need to have, I left it off, gotta be careful, need to have that a there. It's very important. Okay, you can't just drop it off. It's really, really easy to lose track of it like I almost did there. Now if I use my calculator so we can get us a final answer, 6 times 2.71 minus 3 divided by 2 times 2.079, what I get is 13.1415. Okay, that's an interesting answer, but it is a correct one. So 13.1415. 13.1415. And it's as simple as that. So you've got to keep track of your stuff. You can't just type it in the calculator on these. You've really, really got to keep your process. So don't make a mistake of leaving out an A or anything. You've really got to track everything through. If you don't, it could really mess you up in the end. Do the best you can. If you find a different method for doing this, like instead what you could have done is first thing you could have distributed this 3 here. You could have said, okay, that's 15 to the 6 because I'm going to multiply these two. And then that's 8 to the 3 over 2. Then subtracted instead of pulling the 3 out first to begin with. That would have been fine. Like I said, there's several ways to get there depending on which method you use first or which property you use first. If you have any questions, let me know. Other than that, make sure you finish up your homework. And we will get on to the next section next time. Y'all have a good one.